Okay, so without further ado, Joe Grand, take it away.
Cool, thank you. No applause, please. No. I'm going to actually move this laptop over here because I feel weird standing behind the thing, which I will do for the demo, but not yet. Yes, thank you for coming. At least one person gets the reference. My name is Joe Grand. This is what I feel like I look like most days, but I normally just sit in my house and hack on hardware, and once in a while travel to give talks about hardware hacking. I will apologize up front. I just got home from Vietnam last night, and boy, are my arms tired. No, that's not right. I had a I was hoping to be here the whole time for Teardown, but had a last-minute trip to go help some folks with some production manufacturing for a thing that is for a hacker conference later in the summer. So that was a 48-hour trip to Vietnam, and just got home last night, and yes, happy to be here. Just finished these slides, actually, like at midnight yesterday before I fell asleep. And then I overslept also. So my wife woke me up at like 9:45, and she's like, shouldn't you be somewhere? And I'm like, oh my God. So I'm glad I'm actually here and not sleeping. That would have been horrendous. That's sort of like the, I don't know if any of you ever have had this dream of like waking up and, you know, everybody's sitting in class or whatever, and you walk in late, or like teaching, and everyone's, yeah, so that's like my constant nightmare, and that would have happened if she hadn't woken me up. So thank you to my wife. All right, anyway, so my name is Joe Grand. We're going to talk about kind of an introduction to fault injection today. Does anybody get this reference? Anyone know where it's from? Bon Jovi, yeah. So this is the original, the first Bon Jovi, self-titled. And I think Shot Through the Heart is actually the song on this album, not the one that we normally think of, which is like You Give Love a Bad Name, that also says Shot Through the Heart. So, and Runaway on this one, I think, yeah. So this was like a pretty good start, but I thought it would be fun to call the talk Shot Through the Heart, because we're talking about fault injection, and as you'll see, when we're dealing with fault injection, which really is about intentionally causing failures of a device to take advantage of for some reason, usually to bypass some sort of security mechanism or something, we're kind of targeting the heart of the system. We're targeting the CPU or, you know, core voltage on the microcontroller or whatever it is. So I thought that was like a good excuse to kind of do a Bon Jovi cover. Yeah, so that's what it is. So anyway, yeah, this is kind of a quick intro to that. Let's see. So I have kind of some slides about it, and then I'll give a demo, and then I'll talk about some current work as well. So fault injection, really, the whole premise of this kind of goes back to chip manufacturers. In the data sheet, you look in the data sheet, and it's like, you know, we as the vendor guarantee that the chip is going to function within these certain set of parameters, right? So as we're designing a product, we need to look at either the table or the diagram and say, okay, we know that we can operate from 1.2 to 3.3 volts. And if we operate outside of that, above or below, like maybe it's going to misbehave. Like, and we don't want that if we're designing a product, right? We want stability. And maybe for certain voltages, we can only run up to certain frequencies. And that's where the chip vendor will guarantee the functionality. So in this case with the PIC, I just grabbed this one, we see like the gray box. That's where microchip will guarantee that things are going to work. So as engineers, we design within that box. As hackers, we sort of live outside of that box. So fault injection is all about, let's try to do something outside of the original specification where the vendor can't guarantee functionality, and see if we do that at just the right time with just the right technique, maybe we can do something like skip over security check or re-enable some sort of debug interface or get access to flash memory or things like that. So it really is like anything really with hardware hacking, we're kind of taking the engineering tools and the engineering mindset and kind of flipping it. And that's just what we're doing. We're just operating outside of the bounds of things. When we do fault injection, and I'll talk about like some of the different techniques for it, but when we do it, we don't really know what we're going to get. And if a chip hasn't sort of been tested before as far as like what is it susceptible to, are there mitigations for fault injection and things like that, it's a lot of work to actually characterize and figure out, is a chip vulnerable to some sort of fault? But on the good side, there are lots of ways to do it, which we'll talk about, and lots of kind of resulting behaviors. Most of the time, if we're injecting a fault, the system will just crash. The chip will crash, it will hang, it will reset. So it's like, all right, at least it's doing something, but it's not something that we can do in like a controlled way to actually take advantage of it. But once in a while, if we get lucky, we can change some sort of thing during the firmware operation, during the program flow. We might be able to like skip over an instruction by basically like messing up internal logic of the chip and seeing, that happens to maybe the clock's going so fast that whatever internal logic, some of it can't propagate fast enough before the program counter, goes to the next thing or whatever it is. So maybe changing software of some sort, firmware. That could be changing a no to a yes to a no. It could be skipping over an entire check of like, is this computed hash for our code signing valid, yes or no? Like just completely skipping over it. Other times it leads to some sort of computational fault, like sort of data corruption on a bus where maybe something is reading a value, maybe the CPU is reading a value on power up and doing something with that. If we corrupt that value, that could then give us something. So the behavior really you don't know until you start really figuring out kind of characterizing things, which I will get into. I didn't mention, so fault injection, I think in like the computer science term has been used since like the 70s of computer scientists realizing, oh, we can cause problems. Let's use this to kind of validate our systems to create better systems that are not susceptible to those things. And then again, we're just flipping that on our head. Engineers of chip vendors are starting to implement fault injection countermeasures as far as people knowing, okay, we know hackers are going to try to do this against our chip, but unless a device intentionally has countermeasures, it will be susceptible in one way, shape, or form, which is pretty cool. And this technique, once you start doing it, it's like having a hammer, right? Like once you know how to hammer things, it's really, really useful. And you just want to hammer everything. And you can, because there are so many chips available. And it's something that actually is I wouldn't say easy to replicate, because that's a lie. And I'll probably explain that. But you can get going with it, and you can try it. And you can try it with a known example of something that's public, and then you can try something maybe that hasn't been discovered before and use the same techniques and your same framework to go for something else. It's a magical sort of process that even just like 10 years ago was something that I would still consider it an advanced technique. Usually if you're hardware hacking, you're looking for, test points and JTAG interfaces and UART interfaces and things like that. And this was sort of the next level of like, okay, now you need to bypass something. Let's do fault injection. And it used to be you needed much more complicated equipment, maybe even custom tools because there weren't anything available. But now it's something that really is accessible to everybody, which makes it such a powerful tool to use. And we'll talk about some of the kind of tools as well that you can try to use. But it's become something that even though it requires a lot of work and it's kind of a pain and sometimes it's very disconcerting how it works, especially coming from an engineering perspective where like I prefer everything to function the same way every time. But with fault injection, that doesn't happen. So it's a little strange of like, you question yourself a lot as you're doing your fault injection of like, is it gonna work? I don't know what's gonna happen. But so powerful. So yeah, generally when we're doing fault injection, we're targeting some sort of microcontroller security. A lot of times if we're hacking hardware, we say, okay, we wanna get the firmware of the device so we can reverse engineer it. Most devices now have code protection features of some sort. Every chip has different security mechanisms. There's no standard as far as like microchip has to have the same security methods as Atmel, or maybe they will start to if they're, now that they're the same. Or like NXP or other companies all have different security. So it's not like you can look it up and see, one thing is going to defeat everything. So everybody does it differently, which is fine because then we'll just figure out which technique is going to work best for that chip. With chips themselves, so every microcontroller, this was totally mind-boggling to me. I never even really thought about it. Every microcontroller has some sort of internal code that runs before it actually runs our user code. So when we plug it in, we power up the chip, there's going to be some sort of boot ROM that's in the device. So some either code or maybe it's even hardware kind of configuration stuff. But something is kind of executing and configuring the chip. Maybe there is an internal bootloader that sits there and waits if there's sometimes it's a serial interface or USB or CAN or depending on the chip, whatever it is, where you can load new code in case you brick your chip. And then eventually it runs the user code. When we are doing fault injection, typically we're targeting the boot ROM, which normally is where there's going to be some security checks that happen when the chip powers up. But fault injection, if it works on a chip, you can do it at any point in time, which means maybe we're not targeting the boot ROM. Maybe we're targeting some actual user code or the firmware running in the product that's doing some password check or some other thing. So it's not the chip itself, it's the product of whatever the product engineer created. So we have chip level and then higher level. So it's really, really powerful. As long as we can cause the chip to do something, it doesn't matter what level it's at. When we're defeating code protection, which is the demo I'll give you, is about that, where a lot of chips will have some flag or they'll have some setting of don't let anybody access flash memory anymore, disable debug interface so nobody can use it. That's all handled in the boot ROM. If there is some vulnerability that you find or some way to do fault injection on a chip that's in boot ROM, which is hard-coded silicon in the chip, that chip is going to be vulnerable forever, for as long as it's out in the wild. No matter what somebody might do, to try to fix that security problem in higher level code, those devices are going to be vulnerable. And that's what makes this so powerful because, as we know, companies don't really, if you're involved in product development, companies don't like spending additional money, right? The job of companies, they like to make money. So why would a chip vendor spin new silicon if they don't have to, unless there's pressure for them to fix it in some case? One of the devices maybe we'll talk about later is the STM32F2, which is a device that's known vulnerable. It has a couple different options of basically downgrading the security of the device and then taking advantage of the bootloader of some problems within the bootloader, which is also in the boot ROM. And I had emailed them once when I was starting to get into learning about fault injection. And my fault injection wasn't working. I wasn't getting the successes that I saw my friends do in a presentation. I was like, I'm going to try to replicate their work. It wasn't working for me. And I'm like, what is going on? Maybe they fixed the problem, because it's a known thing, and there's billions of the STM32 out there. So I sent them a message, the engineers, and I said, hey, my name is Joe Grand. I'm thinking of designing a product with your STM32F2, but I'm concerned about the security problems that are known with fault injection. Have you fixed those problems? And they respond back and say, hi, Joe, actually, yeah, we're aware of those problems, but no, we haven't fixed them, and we don't plan to. We recommend you use a more expensive, secure chip that has more security features. So instead of fixing the problem, they just tried to upsell me to something else. So it really shows you chip vendors are not going to fix these issues unless they really need to. There was the F4 version of that, where there is actually the bootloader is susceptible like the F2 version, but later revisions, they did change the boot ROM in later revisions of the chip. They didn't document it, but when I compared the boot ROM from the earlier version to the later version, and then we find the sections where we're targeting, which is for the security checks, they've actually built in mitigations for fault injection. And there are techniques to make devices more secure. So I thought that was interesting that they did it for one part of their family, but not all of it. And it probably is because there's some company somewhere that's using a lot of these that forced them to fix it, which is interesting. And that was actually a surprise. So anyway, yeah, we're either targeting boot ROM, user code, or bootloader that's running in the chip. Any place where we want to affect execution. So there are a lot of different vectors that we can use, different kind of environmental or physical access points, I guess you could say, to cause problems with systems. And these really come down to what we have access to on the board, and maybe we just have to try different techniques until we find one that works. So when somebody comes up and gives a talk, or with the demo I'll give you, that looks really easy, hopefully it works, it could be months or years of effort to get to that point of knowing, okay, it's exactly this process with these parameters to do the thing. So take any fault injection presentation with a grain of salt when you see somebody do it. Replicating it is much more difficult. As you'll see, there's a lot of things that play into getting things right. So yeah, we have timing and voltage and electromagnetic, injection and optical and body biasing, all sorts of things. And I'll just kind of go through the main ones that are common, and then we'll go from there. So when we're doing timing fault injection is basically injecting additional heartbeats into a system. So if you think about, every system's going to need some sort of clock, whether it's an internal clock or external clock that's providing the heartbeat for the rest of the system. if we can somehow take advantage of that clock. So if it's an external clock, then maybe we take out the oscillator, we put in our own circuitry that's providing the clock, and then at just the right time when we want to skip over whatever thing that we're targeting, we have much faster clock cycles. So it's sort of like giving us a heart palpitation to like, what's going to happen. And we're just injecting clocks. Maybe it's one clock, maybe it's like 5 really fast clocks, or maybe it's a couple bursts of clock. It kind of depends, and maybe that's going to do something. So if we have access to an external oscillator on a device, that's another potential point. If it's an internal oscillator, we probably don't have any way of controlling that clock. You might be able to do it too. I think, don't quote me on this because I could just be jet lagged, but I think I remember seeing some sort of clock-based fault injection on a system where somebody was able to change some settings of the clock externally or like with software. Maybe it was like some CPU, and they could change the clock settings so the PLL inside was changing, but they didn't have access to it outside. So maybe you could do that of like modifying parameters with the code to get the clock to run faster, but I don't know if that's exactly right. But it would be cool. So timing is common, but not really common. I would say the most common is voltage-based fault injection, and we're starting to move away from that towards electromagnetic fault injection, which I'll talk about next. But voltage fault injection is basically you have your target system, and you find your core voltage line that goes to the CPU, and at exactly the right time when you want to do your fault, you're basically brownouting the power. So you're like shutting the power off really fast. Nanoseconds, picoseconds, for some width of time, and hoping that sort of causes this like, and then like the chip comes back up. So you're kind of shutting it off, but not enough for all the reset circuitry to kick in, and hopefully not enough to like trigger some sort of brownout detection that's on the chip, but you're doing it just fast enough that something happens. This is sort of the first thing generally that people will try is voltage fault injection. One of the two of the downsides, I would say, even though it's very powerful, one of them is you can't really control where that voltage is going on the board. So if you're doing a voltage fault injection, even if you're targeting the core CPU voltage, you're kind of hitting the entire chip. Or if you're going in on your system voltage line, like you could be affecting other things. So you're kind of doing this mass injection, and you're not really able to target necessarily like where or what you're trying to do. It might still work, but it's very, very broad as far as like you're just pulling the voltage line low to ground, and that could affect lots of things. I mentioned like we normally want to target just the CPU core voltage if we can, because a lot of times systems might have 3.3 volts coming in, but then when it goes into the chip, some chips have internal regulators, or if you're dealing with like some more complex processor, you might have your logic voltage inputs. That might be 3.3 volts, but then you might have your core voltage at 1.2 volts or whatever it is. So you might be able to target the voltage you need externally, but we want to always try to target the core voltage if we can. Sometimes we can't, and we just hit the system voltage and see what happens. So one trick, there are some devices that do have only like a single voltage rail coming in, so 3.3 volts, but then the chips themselves have internal voltage regulators because core voltages of CPUs are generally always lower than 3.3 volts anyway. So this is an example of an STM32F, some set. I think it's F2 and 4, maybe some other ones as well, and other vendors do the same thing. So you have 3.3 volts coming into internal voltage regulator, and then that feeds to the CPU core, and that's our target. But the trick that we can do if we want to not inject our voltage glitch on the power coming in, because if we did, the voltage regulator is probably just going to absorb that spike anyway and not target what we need. Most chips that have internal voltage regulators have a requirement for external bypass capacitors for filtering, right, for stability. So if we look at a block diagram of the microcontroller or microprocessor, we look and see, oh, there's actually a spot where we need to attach capacitors. That might be called VCAP or whatever it's called. If we see external capacitors hanging off of a pin, maybe that's providing the capacitance for the stability of the internal voltage regulator. So if we remove that capacitor, now we have a direct input to the core voltage inside of the chip, which is pretty cool. The problem, though, is the voltage regulator is still going to be on, right? We might have an access to the output of it, but it's still on. But you can basically provide a voltage on the output line. If you bring it high enough above where the voltage regulator is supposed to be outputting its voltage, now you can shut off the internal regulator. And now you are providing the core voltage, and then you can glitch the core voltage when you want, which is pretty wild. So yeah, the other thing related to that is when you're doing voltage fault injection, you generally have to modify your target board. So it's a little more invasive around like, okay, I need to remove capacitors. I have to figure out exactly where I want to feed the voltage in and target that. So it's a little bit more prep and a little less, a little more vague in where you're affecting things by just providing a voltage in. But very, very powerful. And that's the demo I'll give you in a little bit. Because some vendors are starting to build in better brownout detection or better voltage-based fault injection mitigations, electromagnetic fault injection has sort of become the next thing. And it's very, very cool where we're essentially still targeting the same areas. We're just doing it in a different way. And we're basically using a device to generate some EM pulse, very, very small EM pulse, that in theory would affect the same way as a voltage glitch, voltage fault injection, except now we can control the X, Y, Z parameters of where we're sending our EM pulse onto the chip to target a particular range. And oh, actually, I have a little video here. So this is a little video. I'm using a device called the chip shouter, and I'm just manually pressing the button to generate these EM pulses. And I'll explain some of the tools a little bit later. But the device I'm just running some code on, so generally it's just printing over the UART like hello, hello, hello. And I have a loop that if the fault breaks out of that loop, then we're going to see something else printed on the screen. So now it's printing goodbye instead. So I'm manually generating pulses. I'm not even doing anything precise. I'm just sort of spewing some EM pulse onto the chip at the correct location on the chip, which I just moved the chip around until I found that it worked. And we can cause different kind of program flow. And this is in user code, not in chip level code. So something like this you would do generally when you're kind of characterizing, is a chip vulnerable to fault injection at all? You try to do it with your own code, something that you can control. So if you have a device that you're targeting that's I don't know, a PIC, whatever, it doesn't even matter what the architecture is. You see that chip and say, okay, that's what I want to target. There's code protection, it's locked. So you basically set up your own environment. You build your own little development tool with your own board. You write your own code for it. You don't enable code protection, so you can kind of step through stuff. And you basically have some loops, one loop and then another loop. And if you break out of one loop, you do something. And then you start characterizing, like, where is the device vulnerable? So very cool. The advantage to EM is you don't need physical contact. You rarely even have to do any modifications on your target board. So you don't have to remove capacitors or anything like that. You just slap it into your little test fixture. You move the probe around, and then you just start sending pulses to the chip. And I'm not a chip designer, but from what I understand, that's a much harder thing to fix because it's not an input voltage coming into something. We're basically inducing currents onto the chip. And what I've learned by doing some of the EM injection is it isn't even necessarily tied to a direct location. If you're like, I want to inject a fault over the section of the chip where the registers are, where the security bit is set, you might not have to target that exact thing. You might be on a separate part of the chip. It just happens that EM pulse where you're doing it propagates to the right spot. So it's not a direct one-to-one correlation of position to what's happening on the die itself. And you might even be just hitting bond wires on the chip that's doing something. But it definitely is way more controllable than voltage fault injection. So this is what we're seeing. And again, there are tools that are making this much more accessible than what it used to be. Another one is optical fault injection. This is sometimes called a paparazzi attack. I've only heard that once, but I think it's cool. Of like, shining the flashes. And has anybody taken a picture of a device that's running with, like, if it's with an EEPROM or like, microcontroller, microprocessor that has internal memory, like EEPROM memory from back in the day, arcade games? I know some of you do arcade games, right? So if you take a picture with a flash of a device that's running that has an exposed die, generally you're going to cause the device to crash or reset or something. So you're sort of you are doing a fault injection. Except in most cases now, we're not dealing with chips that have exposed dies, exposed windows like an EEPROM. We're dealing with devices that are packaged. So this is definitely a more advanced technique, mostly because the equipment is slightly more expensive, but mainly because you need invasive access to the silicon die in order to be able to flash your laser at the right spot. You could do it with a camera flash also, but it's probably not going to be as precise. So this is sort of a benefit of, it's a little bit like EM fault injection where you can really control things, but with a laser, you can really control things. Like you could get to a particular transistor that you want to flip the bit at just the right time. And there's been some wild attacks, like this one, this picture here that I'm showing on the right was from some work from Ledger, who makes a bunch of like cryptocurrency hardware wallet stuff, and they bang on all sorts of other products. This one was from, I think this one was a double fault injection. So they're basically injecting the laser at 2 different times during the process to defeat some secure element. They gave a talk more recently that's a triple fault injection. So injecting at 3 different times, but using the laser so it's so precise at just the right locations at just the right time that they can bypass this stuff. So it takes a lot more work, but the risk is the decapsulation. So if you have to decap a chip, I think there's some guys out here that have been demonstrating that. Oh yeah, the folks that have the X-ray machine also can do decapping. And this is actually from a project, a little board they gave out at hardware.io a couple of weeks ago. That was part of a larger board for kind of some testing, and you could do wire bonding. But if you decap a chip, you have to somehow get to the internal die, and then you have to figure out with your laser where you're going to do the pulse. So the risk is much higher of damaging something if you're doing the decapping, but then the advantage is you have super, super control. And then you can get some lasers online. There are, of course, like high-end, really expensive academic lasers, but apparently you could do it with not as high-end lasers and just some good optics to kind of target down. So maybe like, remember people were hacking with like it was like the DVD laser from a PlayStation or something, like the blue, like maybe that would work through some optics, like a low-cost version. But yeah, really cool. So you can really precisely know where to inject. Then there's a technique called body biasing. I haven't used this. I don't know too much about it, but it basically kind of combines EM and precision of laser, where sometimes you don't have to do as much prep of your device, but you're basically kind of injecting a voltage in at a particular location. And you have a physical probe that's touching down. So kind of like, the laser you can focus on. This sometimes you do on the backside of the chip because there's less silicon or less kind of packaging bulk and stuff you have to get through. So you go from the backside, maybe remove the metal paddle that's there, and then you can target the chip that way, target the transistors or other things on it. And you can kind of use the same setup that you would for an electromagnetic fault injection or laser fault injection, where you generally will have a CNC that you're stepping, location by location and kind of probing things automatically to kind of characterize the chip. But yeah, so there is some work about body biasing. Colin O'Flynn, who started a company called New AE Electronics, who is one of the people probably single-handedly made fault injection accessible to us. He has some work into kind of basic body biasing. So there are all these ways. So if a vendor's like, well, we have mitigations for voltage or EM, it's like, all right, we still have all these other ways. So chip vendors are definitely at a disadvantage, which is always good. I mentioned there are lots of tools to do fault injection. Most of them are created by, I would say, either created by hackers or created by security professionals to kind of target the engineering world of like, here's how you can validate that your chip is secure. And then for us as hackers, now we have a bunch of different ways. And these are basically hardware interfaces. A lot of them are running on, so you have Python, you can control the hardware over Python, and now you can write software scripts to control the hardware. These slides, by the way, will be on my website, which is grandideastudio.com, or just search Joe Grand and it will come up on my website. I do have there's a link, it's like fault injection. Just search fault injection. You'll find it. I think I'll tweet about it also. But yeah, these will be up there with all of this stuff today if I don't fall asleep. So yeah, the Chip Whisperer is made by Colin O'Flynn. This started for him as a PhD project. a bunch of years ago, and he built this basically to evaluate different chips and security and things. Not only does the chip whisperer do fault injection, but it does side channel power analysis as well, meaning you can listen in on power consumption of devices as they're operating to figure out what's going on at a certain point in time and effectively extract encryption keys and things from devices. But we can use some of that basic power analysis functionality to help us when we're doing characterization of a chip to know when we want to inject our fault, which is pretty wild. So yeah, this turned into an actual company. I think he even had at least one thing on Crowd Supply. And maybe it was the Husky. Maybe the Husky was on Crowd Supply. This is, yes, awesome. This is definitely the place to start. He has so much kind of tutorial and documentation around using the device as well. And I do have some resources at the end of the slides also. So yeah, that tool, you have a bunch of Python and you're controlling the hardware, you're setting it up, and then you just let it do its thing as you're running loops. And I'll show you what the process looks like for that. Then there's like the Pico EMP, which is a lower cost version to do EM fault injection. He also has the chip shouter, which is more of the higher end tool. Similar features, but the one on the right, when we see a lot of sort of the public non-academic or non-professional fault injection work with EM, it's using the Pico EMP. So it's a very accessible EM pulse generator using the Raspberry Pi Pico. Bunch of other companies too. So Riskier makes things. They specialize in doing fault injection and side channel analysis. Ledger, like I mentioned, they created their own platform for doing fault injection. Other people have done other things. And the beauty of fault injection, if you're just doing voltage fault injection as just the basic thing, all you need is some way to switch voltages from your system voltage to ground. So you could use a MOSFET or an analog switch or whatever it is to switch between two voltages. And then you just need something to be able to look for some trigger of wherever you want to start your glitch, and then something that can generate the pulse fast enough. So you could really do this with like a couple dollars worth of parts. I'm more of a fan of just getting equipment that I know is going to work. So then when I'm doing my attack, I know that if there's a problem, it's a problem with me and not a problem with my tools. But it sort of depends on where you want to go. There's a range of ways to get into it, which is pretty wild. Oh, then there's a laser setup over there as well. So besides having all of these methods of being able to generate the faults and inject faults, we still need a way to figure out how the hell do we even know where we want to do our fault on a chip. That's the bulk of the work. That could be a career if you wanted to. And people actually are in academia doing their PhD work, on methods to characterize where to do faults or how you can affect things. I mean, it's a whole world now of things. You could go so deep into this. But generally, all we really care about is what technique are we going to use for our glitch? How do we figure out where we want to do it? And then let's do it. So there's a really good resource in explaining different techniques of characterization that's at the end of the slides. But the whole thing is, first of all, we need to know when we need to start our glitch. And that's going to be based on some sort of trigger. Usually that's going to be when like the reset line goes high of the chip. So if we're targeting the boot ROM, we know the boot ROM is going to happen as soon as we release reset, or if there's a power on reset event that happens, reset's then going to go high. That indicates that the chip is now starting to run its own code, its internal code before it runs the user code. So maybe we use the reset line. And then we say, okay, reset line goes high. Now let's wait, some number of microseconds based on some other work. Maybe we have to do some other reverse engineering, or we run a massive loop of trying different times after that reset to see if something happens. So reset goes high, wait X amount of time, and then do our fault. That sometimes works, it sometimes doesn't. There are variances in chip behavior where just looking at an I/O pin or something may not be good enough, but generally we're using a reset pin. It might be something where we're looking at power analysis, and we say, okay, we know there's going to be some timing variances in things of how the chip powers up, or maybe whatever it is, but when the chip starts executing, it's always going to look the same or look similar enough where we can use that as pattern matching. And that's what we might do, is kind of look at power analysis, or maybe we're looking at the EM analysis, so looking at electromagnetic sort of emissions from the device, which might probably in most cases look similar to power, but a non-invasive version. And then maybe use that. And this is where all the legwork comes in. Like this, I'm simplifying this into 2 minutes. if we're doing voltage power analysis on a device, we generally need to add some sort of like shunt resistor that's going to give us a voltage drop across it. So we use a small resistor that we add in line with the power rail, and then we are measuring that on an oscilloscope. And then we say, okay, now it looks like the chip powers up, and then it does, there's a little bit of power consumption that happens. So maybe that's the chip doing some internal configuration. Then we see more power consumption. Maybe that's the user code running. What you could also do is you'd monitor your power analysis while you're running your own user code. And the first thing your user code does is like set a pin high. So you have your starting trigger and then you have your ending trigger. So then okay, this section of the power trace I'm looking at is the chip executing its own stuff. And then as soon as that pin goes high, you correlate that and say, okay, now I know from that point it's running my user code. So if you're trying to target just the boot ROM, you can kind of narrow it down that way. This example on the right is just sort of showing, this is some work from Limited Results, who is a fascinating person. I don't know if anybody even knows who they are. And I think they showed up at some event recently, but sort of low-key undercover. Their whole blog is just hacking things, mostly through fault injection. And it's like no fluff. It's just all this stuff. It's really, really cool. So I liked this example just because it has a nice looking slide. But this is sort of showing when he was doing his research, he looked at the power consumption, which is the blue trace along the bottom. And then he had a reset line. He had some UART as well, which was his own code. So he knew like when the UART started transmitting, he was already running user code. But basically narrowed down for this particular chip that there was some of the security settings were happening towards the end of the boot ROM executing and the beginning of the user code executing. And he was able to narrow that down with a lot of testing. And then he said, okay, I think there's like a couple microsecond window where the security check is happening that's preventing access to the code. And we want to get access to the code, or we want to re-enable the debug interface. So he narrowed it down to some region, and that's based on when reset goes high, then he's waiting, and then kind of running a loop over and over again within this region to try to defeat the code protection. So generally, I found, even with my experience of doing this over the past couple years, being able to use power consumption or EM kind of emissions as your signature of when you want to start doing your fault injection is way more controllable than relying on some external event like a pin going high or reset or anything, especially because sometimes you have to be so precise. And there are situations that you could cause a fault, but you might cause it to do something else, like erase memory of the device instead of re-enabling a debug interface. So there's all sorts of things where you really want to be precise when you're doing this. This is another step of, I guess a visualization of how this process works. We're basically setting up the chip, we're resetting, we're waiting for the trigger, we try our glitch. Generally, that's going to be to check if the debug interface is enabled, yes or no. Are we able to access memory, yes or no, or do whatever our attack goal is? If that works, great, we're done. If it doesn't work, start back at the beginning, adjust our parameters a little bit, and do it again, over and over and over again. So there's a lot of waiting, which is, for me, very uncomfortable. When I'm running a loop for fault injection, and I don't know if it's going to work or not, and you have to wait 12 hours, 24 hours, sometimes even more, that's by far the hardest thing, because I really want it to work. And it's like, then I start questioning, because you have all this time of like sitting there, and it's like, did I do this right? Like, did I mess something up? Is it going to work? And then it works, and you get this massive dopamine hit. It gets kind of, I wouldn't say addicting, but it definitely is like, you get that high, but if it's not successful, you get the low. And then you start questioning everything. And it really is like very bipolar in that way, which is probably not that healthy. Okay, so we'll do the demo. And this demo is based on an attack that Chris Gerlinski figured out a couple years ago. Chris goes to TourCamp. I think he's even done some kind of chip level talks and workshops there. But he's an old school, like Canadian smart card pay TV hacker, and found this attack on NXP, so the NXP family, LPC family of microcontroller, and gave a talk a couple years ago about it. But it's a great demo because it generally works without even trying. So we'll see what happens. But the concept here is there is code protection, and there's a couple different levels of security that this chip can configure itself. And what happens is when the boot ROM loads up, it reads a memory location or a register location, and based on what's in that register is going to determine, like, is security enabled, yes or no. And there's a couple other levels of things that happen also. But basically, like, you can either have no code protection enabled if there's a certain 32-bit value, 3 different levels of code protection based on the other 32-bit values. But if one of these 4 values are not in that memory location, so if it's an invalid read and there's something else in that 32-bit register, then the chip just defaults to being open, which is pretty cool because a 32-bit value is huge, right? It's like 4 billion or something? And there's only 4 valid ones. So if we can cause some sort of corruption with a fault at that time to flip 1 bit out of 32 bits, like, that's pretty good. And then we can downgrade the chip. This is the setup that I'm using, and you can come up and look at it afterwards also, but it basically looks exactly the same as that. I'm using a Chip Whisperer Lite, which is an earlier version of the Chip Whisperer. The Chip Whisperer Husky really is the one to go for, and that's on Crowd Supply. I think he was having some stock issues, component issues like everybody, but I think he's starting to get caught up with that. So I have my Chip Whisperer, which is, in our case, actually connected to our LPC 1114 development board, and you can see some of the wires that are there because I had to prepare the board to remove capacitors and to give me access to the core voltage. Also, what we're doing is we're taking advantage of, there's a serial bootloader on the chip, so we have to pull one of the pins to tell the chip to go into the bootloader mode. Within that bootloader mode, because code protection's enabled, there's a subset of commands that are not valid, like reading memory. If we try to read memory, it's going to say, no, like, you're locked out of that. I have my protection enabled. So that's what we're going to use we're going to target that read memory command. So there's some settings in there. There's like a bootloader enable pin that we have to wire up and everything. So this is sort of the prepared target board. And I have a T connector. So the SMA connector, that's where we're going to feed our glitch into the device. So that's our system voltage. It's not even a core voltage. It's just the system voltage for the chip. In that T connector, one of the sides goes to the Chip Whisperer glitch output. But then because the Chip Whisperer can also do power analysis, the other side goes to the analysis side. So now we can monitor the chip, look at power consumption, and then determine where we want to offset the glitch and then do our glitch, all in the same setup without having to do much hardware modification. Hardware kind of setup of things once it's good to go. So that's what it looks like. And yeah, okay, here, let's just give the demo and see what happens. So I think I'm going to, I have it here, but I'm going to try to mirror the screen so I don't have to keep looking back. And we'll see if you see what I hope we see. Where you're going to see all sorts of other things. Here it is. Okay. Do you see that? Yes. Okay. It's kind of hard to see. This is based on an example that Colin O'Flynn made for the Chip Whisperer, so you can actually find a similar version of this demo on his GitHub link, and I linked to that in the resources section also. So this is running a Jupyter notebook. So basically Python kernel, and we can step through individual blocks to run things, which is really handy when we're doing things like fault injection because we can kind of run tasks over and over again as we reconfigure things. So I didn't test this at all since I got here. So let's see. I'm just going to kind of run through the steps. I'm going to import all of the various Python things that we need. Here I'm going to communicate to the Chip Whisperer. And yep. So now I'm initializing the Chip Whisperer. It's kind of showing us just the default settings and then settings that that have now been set. So now it's showing our settings here. There are a lot of settings, and these are all going to be dependent on your target and how you set stuff up. As far as like, we're doing some side channel analysis also before we do our fault injection, so we're kind of configuring that side of things too. Sort of a lot to explain just for the demo, but hopefully it'll be okay. Here we're configuring like the internal UART of the Chip Whisperer so we can communicate to the chip level bootloader, and then we're configuring all of the glitch settings as far as like the clock speed that we're using, stuff like that. So this Python code also has the library support for communicating to the NXP serial bootloader. So from within this tool, we can communicate to the bootloader, which is what we want because we need to be able to try that read memory command before we actually do our glitch. So let's try to connect to the bootloader. And if everything is set up then we can actually communicate to the bootloader, and it's telling us, like, here's a device ID. So we know we're in there, even though we're only given a subset of commands because there is code protection on here. So there is a whole section in this demo of doing the side channel analysis to see what the power consumption looks like in different ways, to sort of simulate what characterization of a chip kind of looks like. It takes a couple minutes, and it would be really awkward, I think, to stand up here and do that. So I actually ran this last night, and the plots stayed there anyway. So basically what we're doing are these couple phases of power analysis. And the first one that we're doing is saying, okay, this is what you would do on a target on your test board, not on your target board. But this is like, all right, what if I set the code protection value, which is what sets the security state? In this case, it's a 32-bit value, but what if we set that to all ones? And what if we set that to all zeros, which we know are invalid states, but as we're doing our characterization, we say, let's set the code protection register to that value, and then take a bunch of power measurements and see what that looks like, and then set it all to zeros. Take a bunch of other power measurements, see what that looks like, and then take a diff between them. So basically look at just the differences in power consumption from when that register value is all Fs to all zeros. Maybe that's gonna show us some indication of like where in the code or where in the boot process that CRP or that 32-bit value is being referenced, and that might help us narrow down our timing. So that's what this one is. This is the difference with all Fs and all zeros. So we see some spikes that maybe indicate maybe takes more power consumption to work with a 1-bit than a 0-bit, and that's what we're seeing there. So this is something we'll keep in mind. It looks like it's around 2,000 to 5,000 offset from reset. Then we do another round of testing. This one is basically turning on and turning off CRP, the code protection. So in one state, we'll just set it to some undefined value, and then the other state, we would turn it on. And in this case, we're using the same Hamming weight, so the same number of ones and zeros. So if there is any power consumption difference with bits, it shouldn't show up as much in this case. And we just want to see, again, as the chip is booting, when it's acting on that CRP value or on that 32-bit value, if the code protection's disabled and with the code protection enabled, what does that difference look like in power consumption? Maybe that's going to show us like it's checking the state of code protection and then it does something else. So we might be able to narrow it down. And again, this is just like an example that would generally take days or weeks to kind of figure out what's useful. So here we see some other activity. It's not as obvious any bigger spikes there, but there are some slight differences between code protection enabled and disabled. Sometimes you see a very obvious thing of like maybe the chip doesn't even have any significant power consumption versus yes it does or something. But this is a little more vague. If you overlay the two traces of our two different diffs, we can see the bigger spikes of the first trace and then some of the smaller ones. It just happens that kind of based on some other research that Chris did, this region here between like this large spike, actually it's even more of like these two smaller ones, but somewhere in here is where like that range is where we want to target. But again, generally you would spend a lot of time doing this characterization, or somebody else would do the characterization, and then you would know how to set it up to actually do your glitch. But I just wanted to show you this as like, you can do it with an oscilloscope as well, but having it in code where you're doing this really helps, especially if you're dealing with the same chip, but multiple products or something where the power consumption is going to be the same, but your timings might be different. Then you can run this during your fault injection sort of campaign and say, okay, there's variations in the chip. Maybe the environmental temperature is different or whatever, but the offset's different. Let's set that offset range to then do our attack. So side channel analysis, super, super powerful when you're doing characterization. But let's do the actual fault injection now. So here we're going to verify that we can communicate to the device, which we saw that we could. And now we're going to actually try to read a block of memory. And this should say, okay, we can communicate, but then it's like, no. Code read protection enabled. So this proves that the chip is actually locked and that I'm not like totally faking this. So we're trying to read memory, we can't. Now we're going to do our glitch. So here we're setting the range of things that we're targeting. So the first one is the offset range, so 5100 to 5300. So if we go back up to our screen here, like maybe this is like 5000 kind of right here, and then 5300 is here. We could let it run longer. Like if our goal is to just cause a fault successfully, we just let it run overnight or whatever it is.
So you could have a wider range. There was some work I did when I first got into fault injection, which was hacking the Trezor1 hardware wallet that was voltage fault injection on the STM32F2. And I didn't know the range very much, so I just let it run for hours until I hit it. I've been able to kind of narrow that down now, but you don't necessarily have to know right away the exact perfect offset. But here we're going to set it up. And then we're going to basically run this loop where the chip whisperer is going to reset the device. It's going to try to read memory. If the memory is not successful, then it tries again, changes the settings, tries again. If it's not successful, change the settings, change the offset, try again, try again. What's also here is like if you run through the whole offset range and it doesn't work, then the chip whisperer adjusts the width of the glitch. So since we're doing a voltage glitch, we're pulling the power. So we try it at a narrow width, and then we do it again at a slightly wider width and a wider width. Eventually, it's going to be so wide that the chip's going to crash. But that width matters, and the offset matters, and environment matters, like all sorts of things. All right, so let's run it. So it's running the code, it's doing its offset with the width, and it's trying to read a memory region, and it's saying denied, denied, denied. So we're doing these glitches over and over again. If we had an oscilloscope, we'd be able to actually see that voltage rail glitching every time. I'll show you what it looks like afterwards. But it looks like it's, so we might have to wait, and it's trying to read, and as soon as it's successful, it's then going to read from like memory location 0 to whatever. It's just going to dump everything. But it's like, okay, awkward. I'm just kidding. So it's trying. So I mentioned a little bit that when you're doing fault injection, everything matters. Like the length of your cables matter, especially if you're doing voltage fault injection. Other techniques, maybe not so much. So in this case, it's like, it might eventually work if we sit here. But I'm going to make a little hardware modification to this board and show you why this fault injection stuff can be so infuriating. Okay, so we're trying it. It wasn't working at all, blah, 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 and then I aborted it. It turns out, well, here, let me do it first, and then I'll explain it. Okay, so I just made a little modification. I took off the T connector that was then connected to the capture side of the Husky. That's looking at the power analysis side, because we don't really need that. We just need the glitch output. So now we just have, instead of that T connector going to the target board, just a single cable going from the chip whisperer, glitch output to the core voltage line, or to the voltage line that we're glitching on the LPC device. So just took off that other side that we're doing the side channel analysis of. And now let's run it again. Oh, what did I break this time? Oh, did I disconnect it? All right, here, let's just run, the initialization again. You get to see fault injection in real time. Oh, okay, good. And these are the things that you'll go through and you'll spend like hours pulling your hair out about like, what didn't work? Set this up again. Try to configure it again. Okay, so I didn't like mess something up when I did that. Now, skip over the side channel stuff. Okay, configure a fault injection again. This is gonna read. Invalid. Set the range. Okay, maybe I messed up some variable when I stopped it. Okay, is this gonna work now? Okay, so now it's like so it tried and like, first attempt it worked. So, and now it's actually dumping the code. So it's reading a block and dumping the code from the device because now we've defeated the code protection. And again, the reason that I chose this particular device as the demo is it is so susceptible. Normally, your first glitch is not gonna defeat the security. But if you get your settings right good enough, it's gonna work. But this shows that everything matters. Just that extra T connector affected the quality of the glitch enough to prevent the glitch from working. And that's something, if you don't know that and you're going into a system with an unknown set of results, it might be something like that. Like if you change your cable, it's gonna change everything. And that's the hardest part, I would say, of fault injection. But here, it's now gonna just dump the whole code, which is pretty cool. So this is what the voltage glitch looks like. It's kind of hard to see on the screen, but with the T connector. So we're basically glitching our voltage down to zero, down to ground. And that's called a crowbar glitch when we use a MOSFET and we're basically shorting power to ground really fast. So the glitch is going down to ground, which is fine. It looks like a fine glitch. It's just not giving what we want. But if I take the T connector out, now our glitch is actually going below ground a little bit. So it just happens that kind of the strength of the glitch, in this case, having the glitch go below zero, and it could even be sometimes like the settling that happens after the glitch plays a factor into what happens. So it might not even be the glitch itself. It might be what happens when the power rail goes back up. And these are all sorts of things that happen, but you can kind of see this very, very small change, right? It's like a couple tenths of a volt is all it took to make the glitch successful versus not successful. So here are some resources. The PDF that I'll put on the website, it has linkable whatever links. You can click on those and actually go to places. But if you want to get started with fault injection, the Hardware Hacking Handbook is a book that Colin O'Flynn wrote with Jasper from Riskier that goes through, actually, this is one of the examples that it goes through, but it has a bunch of different experiments with fault injection, which is pretty cool. Taking the Guess out of glitching is Major Malfunctions talk that really talks about how to do proper characterization and the different tips and tricks you can use when you're dealing with like an unknown chip of how to get it set up to help you figure out where you want to do your glitching. And then a bunch of other links to people that are doing like really interesting stuff with fault injection. So sort of the summary of this is fault injection is awesome. It can be extremely frustrating, but very, very powerful. Most general purpose microcontrollers that we see in products, if there is security, it's not that great. And there are probably ways that we can defeat it. Unless the chip has intentional security mechanisms against fault injection, we can probably take advantage of the chip. We just saw that fault injection is dependent on lots of factors, so it takes a lot of time. And really, I would say the engineering mindset of like, let's try every possibility and let's wait and try different things and document everything to do it. And then, yeah, when it works, it feels like magic. Thank you for coming and listening.